Hi everybody, so thank you very much for coming today. So it's a great pleasure to introduce Amanda Prorok for the next seminar on the robot learning seminar series. So Amanda, as you can see, is Professor of Collective Intelligence and Robotics at the University of Cambridge. She's going to be talking about graph neural networks and multi-robot systems. Amanda's somebody I've been wanting to come in and talk for quite a long time. I think I asked you about a year ago, and we've just managed to find some time now. So thanks so much for coming. I'm really looking forward to your talk. And there'll be some time for question and answers at the end, so feel free to ask some questions at the end. And Amanda, over to you.
Thank you very much, Ed. Thank you. Hi, everybody. Thank you very much for coming today. And thanks so much, Ed, for the generous invitation to come over. It's always a huge pleasure to come to Imperial College. So today I'm going to be talking about graph neural network-based interaction models. I'm going to be focusing on collaborative control in multi-robot systems. And let me just start out by giving you a little bit of an overview of the mission of my research and what we do in my lab. So it's a very special time in computing where we're being driven by a confluence of AI and communications and also mobile computing. And I really believe that the next wave of computing is going to be about agents that communicate and coordinate. So that's kind of the general idea behind a lot of the things that we do in my lab. A little bit closer to what's actually happening today in terms of applications, we are already seeing various deployments of multi-robot systems in actual real-world applications. And these systems are progressing towards ever more complex engineered systems. And you see robots interacting here, and they're helping out with tasks that are not only requiring spatial distribution, but simply need some or benefit from some coordination amongst the robots that contribute to these to the solutions of these tasks. And there are many benefits that multi-robot systems can provide. They can alleviate some pressures of urbanization. They can alleviate the pressures of dense living, and also help in monitoring or taking count of what's happening in the environment through environmental monitoring. So this is a little bit of the backdrop of what motivates us from an application point of view. And what we really need to do as researchers is think about solutions for multi-robot systems that can be deployed to these systems or to these applications, but they need to be adaptive, efficient, and resilient because we want them to survive and be robust and reliable once they're out there operating their duties. So how do we actually achieve seamless coordinated behavior amongst multiple robots that are interaction? And I like thinking about this in terms of what I call the 3 C's. So the 3 C's are coordination, cooperation, and collaboration. And I would argue these are 3 slightly different things if you think carefully about them. So coordination is something where we're thinking of problems such as, like, for example, multi-robot coverage, where we can gain performance as a function of the number of robots we're deploying in the system, but it's sublinear in terms of performance gains as a function of the number of robots that are participating in the system. Cooperation can give you higher gains, so potentially superlinear, but there might be a threshold effect. So you can think of cooperation in traffic or cooperation for connectivity in coverage control. So those depend on a minimum number of robots that are participating in the scheme so that you actually see the benefit. And then there's collaboration, where we see gains in performance, but there's interdependencies between the robots because they're different. They're heterogeneous. They provide different complementary skills towards the solution of the task. Now, if we think about this in a learning context, we can also paraphrase these things in terms of the reward function. So coordination, we're thinking of individual objective functions where there could be potentially any degree of alignment amongst the agents. In cooperation, we are thinking of an objective function where there's a shared goal. And in collaboration, there could be a shared goal, but there's interdependencies between the individual value functions that the robots are adhering to. So that's a way of translating what these different paradigms translate to in the context of defining an actual learning problem. So why is this an interesting research program? Why do we even have to study this problem? So the main thing is actually solving the 3 C's is really hard. And this really leads to the core problem at the heart of my research. So what we're interested in is really designing practical methods for effective collective multi-agent systems. And why this is hard is, well, there are a couple of reasons. First of all, we can think about modeling the systems as fully observable centralized systems. That would be one good way of going about developing or devising solutions. But if you do that, then you have to somehow circumvent or deal with the hardness problem of coordinated decision making. So many centralized formulations tend to be NP hard, and then you have the coordination problem that you have to somehow disentangle. So finding solutions that run in real time for larger systems becomes the new challenge. If you do distribute the systems or decentralize them in some way or another, you alleviate the computational challenges. So the hardness part goes away a bit, but then you're facing partial observability. You're looking at a decentralized system. And because of that, if you still want to leverage some form or another of information aggregation and recomposing global state information, you have to think about how is information shared. So this leads to the problem of communication and the question of what do you communicate, to whom do you communicate, and when do you communicate. So that becomes the new research problem. And even if we can solve these first two boxes, then there's the problem of transitioning these solutions to the real world, where obviously we as roboticists know through firsthand experience, you deploy the systems into the real world and everything goes differently than as expected and as planned. So we need our solutions to be robust to noise that we perhaps didn't model correctly, to delays and faults, and perhaps even to non-cooperative robots and adversarial components that we potentially didn't include with certain threat models that perhaps should have been included in our systems. So these are the three pillars that make this an interesting research program, and there's quite a bit of work to be done in solving all three of them. So we can either tackle them through first principles-based approaches or through data-driven approaches, or perhaps even a combination of both. And in today's talk, I will be mainly focusing on data-driven solutions and how we use them and partially also combine them with first principles-based approaches. So let's talk a little bit about how we go or how we think about learning to coordinate, cooperate, and collaborate. So the key question here is, can autonomous agents learn to work with each other? Okay? And so the key idea here is that we're going to be representing the agent-to-agent interactions as graphs. So our graph topology is going to be acting as a proxy for the interaction topology. And that's really key here because we're going to be exploiting the structure of the underlying data that results of our learning process as our inductive bias in the learning process. Right? So the graph topology is our proxy for the interaction topology, and that really helps us design the learning architectures. So once we've done that, what is it that we actually want to learn? Well, we want the agents to be able to model the interactions with other agents. We want them to learn what they're supposed to be communicating in different situations as a function of the underlying downstream task. And we want them to be able to make decisions based on the information that they received or based on these interaction models that they have conceived a priori. So that's the overarching goal. So let me talk a little bit more about the maths, the foundations behind it, and how we go about this. So what we do is we begin by considering how we can actually model the interactions between two agents. So here we have a robot J that makes an observation, and we want to understand how that observation of robot J impacts the action of a robot I. And we're interested in representing how what we call this interaction feature Z sub J is processed by agent J and how it influences the action of robot I once it's received by robot I, and what kind of decision that leads to in the system. So this is kind of the basic way, high-level view of how we model the interaction scheme. Furthermore, we can take that very same model and we can now extend it to, or generalize it to an arbitrary number n of robots that are in the neighborhood of our robot I. And the only thing that changes here is that we have some means of actually aggregating the interaction features that are coming from my neighboring robots. So the aggregation scheme here is really core to the architecture that we use in what we do. So now we're going to formalize this, and what we do is we simply say, well, the robots in our systems are the nodes in our systems, right? And we immediately arrive at this graph abstraction of the interaction topology. The robots are the nodes, their interaction links are the edges of the system. And what robot I then can do is simply model the interactions through the hidden feature h sub I, which I already introduced before, which is now the result of this function phi that aggregates these incoming features in a permutation invariant manner. And that's important because the order in which the information arrives at robot I is not important, right? So the graph topology here is our proxy, and it induces that nice inductive bias on our learning architecture. And what I'm showing you here in this mathematical formulation is actually very general. It's trying to capture all the various flavors of graph neural networks that are out there. And there are many different instantiations of graph neural networks. So this is a general way of writing one down. But to be a little bit more specific, I'm going to give you an example of how you can translate this to a graph neural network with actual operators in place. So if we assume that the aggregation function is given to us by a sum operator, and the interaction topology can be described by an adjacency matrix, then we arrive at something that's called a graph convolutional network. And what that allows us to do is we then conveniently write out the system in matrix form. And if you look at this equation here on the right-hand side, you see our nonlinearity, and you can see how this equation inside here, so K is actually the number of communication hops or interaction hops in the robot topology. We have our adjacency matrix, we have our features, and W is simply the set of parameters that we're trying to learn here. So everything is very nicely exposed when we write things down in this matrix form. And so now we know the parameters that we're trying to fit. If at train time we can observe the topology of the interactions, we have all the information that we need to actually tune these systems. So I'm going to start giving you a couple of examples of what we can do with this very general framework that is given to us through graph neural networks. And the first thing we're going to do is start by just modeling interactions between robots for a very specific purpose. One of the things that we've been interested in tackling in my lab is close proximity flight. So if I look at this example here, what you see happening is there's a hovering drone, and there's a drone that is tasked to drive or to fly in a straight line underneath the hovering drone. And what happens is that the robot in flight is affected by the downwash pattern of the drone that is hovering above it. If we want the robot to drive in a straight line, then obviously we need some sort of model that models the downwash forces as a function of some information that we know about the system. So in this case, it would be the relative positioning to the hovering drone. We can then compute that force in real time and include it in our control scheme that is running at a high frequency on board the robot that is in flight underneath the hovering drone. So that's ideally what we want to do. So if we look at first principles based methods, we have to start leaning on to models that stem from fluid dynamics, fluid mechanics, aerodynamic research. These models typically don't run very quickly, and certainly not on a Raspberry Pi computer, which is what we have running on this drone in flight. So that is why we look to machine learning, and why running inference with a model that actually fits onto Raspberry Pi is very interesting to us. And so this is kind of the backdrop of why we tackle this problem with our solution. So here is the actual model. We have the dynamics model of the drone that is of the sufferer drone, and we want to estimate this external force so that we can include it and counteract it within our controls. And what we now do is we take our interaction model, which I introduced before, because it basically allows us to model what the other nearby robots are doing. And we're simply going to try to learn the parameters of our function phi in a supervised manner. And we can do this in an indoor setup because we can track the robots with ground truth information, and at train time we can actually produce labels for these kinds of systems. So we have a way of training these systems in a supervised manner that is quite precise. The requirements we have of our model is that it's going to be able to predict forces in 3 dimensions. So there's been some work on forces up and down, but we were also interested in lateral forces. The model must be fast because we're running high frequency control loops here, so it has to be able to run at least 50 hertz. And it has to be small because we want it to fit on a relatively constrained embedded computer on the actual drone. So those are our conditions. So how would we go about the problem? Well, as you can imagine, aerodynamic patterns are complicated. And we actually used a trick in our system to try to simplify the learning process, to reduce the amount of data we needed to collect in order to get data points for all the possible aerodynamic disturbances we could have, as well as reduce the size of the model. And one really elegant way of doing this is by exploiting symmetries in the system and designing neural network architectures that implicitly represent these symmetries. So what we do is we use the intuition that in the frame of the leader robot, so the hovering one, there is actually a very nice symmetry we can exploit, which is equivariance of rotations around its vertical axis. So you can see that actually these two drones that are coming from different angles, they will be experiencing the same force, just rotated by a certain degree. And this is something that you can bake into very elegantly into your neural network architecture, and you get, essentially in the symmetry group, you get an infinity of essentially efficiency of a data point, because once you get one data point on a plane, it counts for all other positions around that same plane, because it's just rotated and the force is actually the same. So in terms of data efficiency, this is a very smart trick to do, and we definitely decided we'd be interested in exploiting this. And we managed this, and it turns out that the neural network then is able to predict patterns that make a lot of sense and correspond to ground truth information. So what's really cool is then, by having this equivariant neural network, we are able to satisfy the conditions that we set out to achieve. So we have a model that is producing three-dimensional force predictions. It's very small, less than 300 parameters, actually significantly less. It just has one layer, and it's very fast because it's small and it fits very nicely onto our Raspberry computer. And so in this movie, what you see happening here is the blue robot is now running the model, the red one is not, and you can see that we are significantly able to reduce the amount of downwash that is experienced and executed in the controls or the trajectory tracking of the robot that is now using the model. There are a couple of things that you can do with this model. So driving in specific formations is great, but there are applications that actually require this. And one of the things that we did, this was led by one of my postdocs in the lab, AJ Shankar, was think about, well, docking, because docking is a really hard problem, actually. So if you look at this movie, you see the hovering robot is actually carrying a pole, which you want the robot that is flying underneath it, so the follow robot, to dock onto. Docking can be used because you need to charge or you need to transfer goods. There are many other reasons you might want to be able to dock. And you might think, okay, the intuitive solution is, well, just make the stick longer if you can't fly accurately at tight distances because of downwash, right? But the problem is you make that the docking contraption bigger and longer, and flight becomes more unstable for the drone that actually has to carry the docking mechanism. So it's a trade-off that isn't really clear which solution, which way you actually want to go. But now that we have a downwash solution, we can actually shorten the docking, the size of the docking mechanism, and try to improve the actual docking procedure. And so here you can see a movie of when this is actually done. So this is in a test where we have Alpha, which is our drone, and now using the docking mechanism, you can see that the robot is able to keep its height and actually dock, and then also successfully undock, which is also a difficult procedure because you have to maintain stable flight and unlatch the mechanism and retreat and open up the dock. And here you can see it in free flight, where we have autonomous two-vehicle docking. And at some point, there's also a clip showing you what happens when you don't use the model, and that it just simply misses the docking pole. Oh, possibly cut that. Yeah, okay. So I was talking when it showed. So if you don't have the model, it's not able to maintain stable height and misses the docking pole. So this is really cool, and we're now able to use this pairwise interaction model to counteract the downwash forces. But you're thinking, okay, well, what we're actually interested in is doing this maybe not only for pairwise interactions and two robots. What happens if we start scaling it up, and how does the learning paradigm actually translate to that? So the next thing that we started thinking about is, okay, so how are we actually going to model aggregate forces? So if we have multiple hovering drones or multiple drones in the vicinity of what we call the sufferer. And the main question here is, so yes, maybe the force is going to be higher, maybe it's a simple aggregate, maybe it's a linear aggregate, but maybe it isn't. And we don't really know what model is going to be the right one to use here. So there's two things we came up with. We said we'd start by evaluating two hypotheses. So either it's going to be a linear model, and we can simply sum the individual interaction forces. And the reason that that's a very attractive hypothesis is because you can train pairwise. And then when you deploy, it generalizes because you're just modeling a linear system. So in terms of training, that would be very convenient. The other case would be it's a nonlinear model. And in that case, we're actually explicitly going to be accounting for some sort of nonlinear effects as you scale your system, because we're assuming that the relationships are actually k-wise, potentially even dependent on the actual specific robot formations. And we're going to have to represent that through some universal set function approximation function, right? So we can't take the shortcut of just assuming a linear model. So those are the two hypotheses we had. And we set about trying to evaluate these two hypotheses to see which one it was going to be. And so Jennifer, one of my PhD students, very gifted, came up with a 6 degree of freedom load stand setup, which was designed to actually gather ground truth measurements of the forces felt over 6 degrees of freedom. So 80 hertz measurements. She included isolating and damping couplers and in order to isolate the various degrees of freedom. And she also made sure that that drone in hover mode would represent a zero load, so absolute baseline, and anything that it felt was going to be due to any downwash felt from any robots in its vicinity. And so this is the setup that we use to evaluate what happens when you're flying groups of robots around the sufferer drone. And so we then went and we collected data, and all the possible formations we thought were relevant that would produce different downwash patterns. So lateral aggregates, stacked aggregates, laterally shifted aggregates. So here you see 2 flying over, now here you see 3 flying over the sufferer, because we were also interested in, well, are there nonlinear patterns when the downwash mixes in weird ways with the downwash of other robots, right? And then how is it felt by the sufferer drone? So these are all the artifacts we wanted to somehow capture and measure with this 6 degree of freedom load stand. And so we made a couple of insights. So the first one that we made was, well, actually it turns out that downwash functions seem to be very narrow as you increase altitude over the sufferer drone. So they're very concentrated if your formations are hovering over the sufferer drone. The other insight we made is it tends to be easier to model in closer proximity. So this is an error plot for movement around the sufferer drone at, I think, 30 centimeters, and this is about 3, and the second plot is about 3 times that distance. And you can see how the ground truth starts to deviate significantly from the naive linear and single model. And what we also found, and this is perhaps the most interesting one with respect to our two hypotheses, is that on the right-hand side, you actually have ground truth information. And on the left-hand side, you see what our linear model is producing for 3 hovering drones. The downwash patterns do not merge linearly. So the interaction between the downwash when you have multiple hovering drones does not seem to be just a linear function of the individual downwashes, kind of confirming the hypothesis that in certain regimes, we need to use a nonlinear model to capture the actual downwash pattern. And there are more quantitative papers, results in her paper that was presented at ISER last year, showing how overall the nonlinear model does seem to do a better job of capturing these interaction forces. But it is a trade-off. So the training is definitely more complicated, but in certain regimes, and if you know what flight regimes you're going to be flying in, it definitely pays off to be using the nonlinear model. So much for modeling interactions between robots, and I now want to talk a little bit about something that is also very close to heart and was a significant part of some of the research we've been doing, which is using graph neural networks not only to model interactions, but to synthesize interactions. And what I mean by that is basically synthesizing the actual messages that the robots are sending each other. So here we're simply viewing the graph neural network as a way to create a differentiable communication channel. And we're going to use these interaction features that we're producing through this training pipeline, and we're going to be conditioning the downstream robot, so the robot that's receiving this information, we're going to be conditioning its actions, its policy on those observations that have been encoded through this learning architecture. So basically stringing together all the elements, which here are, we have F of O, which is simply processing your observation, phi, which is our graph neural network, and pi of O is then our policy as a function of the original observation that is made by any robot in the neighborhood. Streaming those two together, we now have basically two things. We can define how outgoing information is being encoded, and we can also define how the incoming information at any robot is going to be processed. So at both ends, we now have a handle on how communication is being defined in robot groups. So now you might ask, hey, why is learning communication interesting? And I did touch upon it in my motivation, but I want to give you a bit of an overview of what the community has been thinking of within this domain. So what I'm showing you here is a kind of a cartoon that represents problems as a function of how partially observable they are and how large scale they are, how large their configuration spaces are. And you can see that here in the center we have offline optimal solvers, which are really good for systems that are not so big and that are fully observable. So for those, plenty of optimal solvers exist, and they can compute very effectively, very quickly, because the scale is relatively small. Think of multi-agent pathfinding solutions or traveling salesman type solutions, which are then optimal and very well established area of research. As we scale up in terms of partial observability, we can also solve these problems quite effectively with, for example, frameworks given by POMDPs, but also only for rather small systems. As we go into the larger regime, we're looking at offline approximate type solvers. So again, TSB, but there are very many very effective and very near optimal solvers that exist for very large scale systems and that are largely accepted by the community and produce accepted results that tend to be qualitatively very good. But what we're still missing is solutions that are running online in real time for very large systems where we have partial information, where potentially we need to impose a decentralized structure. We have a global objective we still want to achieve because we want the robots or the agents to be contributing to one higher order goal. And we need the system to be resilient at a local as well as a global level, all these things coming together. That is a box that is relatively poorly addressed by research currently done in the community. And so that's why what we're interested in, and that's really where learning comms comes in, because first principles-based methods don't really make the cut here just yet. So I want to make an example of a kind of such problem that we looked at. So this was something that I did pretty early on when I joined Cambridge as a faculty member, and it was the first problem that we actually set ourselves when we started thinking about solving really hard coordination problems and how we might use differentiable communication to help solve them. And the question we were interested in answering was, well, can we somehow automatically synthesize local communication and decision-making policies to solve something that's really hard, so that is accepted by the community to be an NPR problem for which only approximate offline solvers do a good job. Our goal here was to derive a local policy that was based on only local observations and local comms, no global observations, fully decentralized, yet we wanted that policy to somehow approximate or be near optimal in terms of performance and hopefully also reliability. Yet scale very gracefully as we extend it to hundreds of thousands of agents, and thereby beating the performance of what current standard off-the-shelf optimal solvers can do. And so here you actually can see already the solution of our system, and what you should be thinking here is, well, this is actually decision-making in real time. Every agent here is running its own process, its own little GNN. Every agent is aggregating information that's coming in only from a local neighborhood. So if you focus on one agent here, the edges actually represent the information coming in from its neighborhood. And all the agents have to reach their goals, and they have to do this without getting stuck anywhere in live locks or deadlocks. So that's the goal. And there's no offline a priori planning or computing it whatsoever. And here the robots only get what they are seeing in real time. So how do we devise the architecture? Well, we start with a local observation, which is really just a small snapshot of what the robot can see around it. The robot doesn't even have its global position. It just sees what's around it, and it has an orientation towards the goal where it needs to go. But it's all relative with respect to its own position. We encode this local observation with the CNN, of which the parameters are being learned as part of the learning pipeline. The communication is going to be learned through a GNN, and the output of this is going to be our action. If you want, you can also have an MLP squeezed in between the GNN and the actual action, but both architectures are completely valid. And then here again, using the same notation I showed you before, basically the action is just going to be conditioned ultimately on the observation that any robot is making, which is within communication field range of the robot that has to make the decision, right? So it's being conditioned on those observations within the neighborhood. So fully decentralized, and it's a decision-making policy, so happening all in real time. So here's the results. So what you can see on the left-hand side is an actual expert solver playing out the solution that has been computed a priori offline. Okay. And on the right-hand side, you see the very same instance of problem being solved in real time through our system, through this decision-making policy, using only local comms and observations. So obviously a lot going on here, but qualitatively what you can see is that the robots on our solution, they reach their goals at roughly the same time. There are no deadlocks, there are no live locks, and we show in these examples, these are successful examples, we achieve completeness of the system. What is going on under the hood, or how we achieve this? Well, we use the paradigm that is called centralized training, decentralized execution, by which we take optimal solvers to compute data sets for us. We train our policies to understand how communication has to be generated, and then we take that communication policy and we deploy it on instances of new problems that haven't been seen before, and we can scale to much larger problems than those we used and were seen during train time. So transferability and generalizability is really important here, because that's where we're providing a benefit over optimal solvers that can already do small-scale systems very well, right? And because everything's running in real time locally on board the robot, we don't have a scalability problem anymore. It remains O of n, where n is the size of your neighborhood, and that's the size, and that's where it stays. So computationally very elegant. And so the other thing we basically are interested in showing is that we have a graceful performance drop-off as we generalize to larger and larger instances, or to instances that are very different from what we saw at train time. And the results in the paper do show that we have these graceful performance drop-offs. There are performance drop-offs, and there are ways of getting around them, and we've looked at a couple of different mechanisms, but they tend to be quite graceful, and there's no point at which we see, oh, there's a major problem with this architecture. So the general idea bears a lot of promise, and what I find particularly interesting is that the setup of the paradigm is so powerful in the sense that it's fully distributed, decentralized, and requires no information a priori, which means that it's robust to anything that can happen in real time to the actual system. So if you imagine this is an actual warehouse, changes in the layout of the obstacles and so on and so forth have no impact, because it's being integrated at real time and being solved for in real time. One thing that we definitely have to look at, and is part of some of my ongoing research, is optimal solvers, optimal conventional solvers give us guarantees on optimality and completeness. And this is something we are not quite ready to do yet with most of our neural network-based solutions. And that obviously is a big, that is really important, because if you imagine you're Amazon or one of these providers of warehouses, you need to know that with 99.9% of probability, there will be no deadlocks or live locks in your system. Because if there is, you have to shut down your warehouse, and it'll cost you $1 billion per second, right? So that's something that's also close at heart to us, and we're definitely focusing a lot of effort in that area of research right now. So let's dig a little bit more into the path planning problem. And I want to talk about path planning now in the continuous domain. moving on to real robot systems. So before we talk about that, let me just take a step back and describe you the differences between what a coupled planner can do and a decoupled planner. So as I alluded to before, coupled planners are those that can model the systems in a centralized way. They provide completeness and guarantees. As soon as you decouple the system and you decentralize the information, it becomes a little bit harder to provide those same kinds of guarantees. Now, what we are interested in is decoupled planning. We want to do this in the continuous domain because we have our robots mostly don't move on grids and on chessboards. We want to be able to do this in cluttered environments using decentralized controllers. So this is the combination of attributes or requirements we want our next solution to be able to address. So we looked into literature and peeled out one of the most promising state-of-the-art approaches towards this problem, which is combining a control Lyapunov function with a control barrier function. So the control Lyapunov side of things in the continuous domain guarantees reachability of the target. So it guarantees that you will always be progressing to your endpoint. So these robots here, although you don't see it happening, are tasked with going to the other side of this constriction in my lab setup. The control barrier side of the optimization function provides a guarantee on collision and deadlock freeness, or collision freeness. So it ensures that your robots will never collide into each other or into any other obstacles. So it's a safety guarantee. And combining these two constraints into a continuous optimal control problem gives us all the guarantees we would want in order to run these kinds of robot systems in a continuous workspace. Now, what's happening here is we're taking the state-of-the-art solution and we're taking a state-of-the-art method to tune the CLF-CBF paradigm, which basically they depend on several parameters. We do an exhaustive sweep of the parameter space, and this is the best it can do for us. And what's happening here is you can see that for this particular setup of the environment, with the robots running the same parameters that we tried to tune exhaustively, the problem doesn't complete. And the reason it doesn't complete is because they get into a deadlock at the constriction because they cannot deconflict with respect to each other how they are supposed to prioritize to get through this narrow constriction. And the CLF-CBF paradigm doesn't provide a ready solution in order to get around this. And so this obviously is not satisfactory, and it's a bit of a gap in the literature. And so we started thinking about how we could solve this problem. And one of the things that we realized is that what's missing to a large extent is CLF-CBF paradigms that allow you to tune these parameters in real time. So tune the parameters that they depend on in real time as a function of what formation your system is actually in. Because it seems like, by watching this, that given that all the parameters are fixed and static, there is no input of contextual information that would allow them to deconflict as a function of the current status of the system. So here's a formulation of the problem. So we have flow functions f and g that define the agent's dynamics. And what we want to do is we want to generate controls u that allow us to solve a QP so a quadratic program at every time step, where we're trying to minimize the control effort of the robots. Now, this quadratic program, without going into too many details, has two constraints. As I already alluded to before, the first one is the control barrier function constraint for the collision freeness, and the second is the control Lyapunov function that basically ensures that all the agents reach their goals. Now, what's interesting in the CBF portion of the constraint is that we have this function alpha, that is a class kappa or class K function, that depends on two parameters, zeta and eta, that basically tell us how strictly we're trying to enforce the safety of our system. So how much slack we're going to give the robots as they try to navigate through these scenarios. And these are the two parameters that I mentioned before that need to be tuned for any system that runs a CLF-CBF-based control. So what do those two parameters mean if we try to interpret them? Well, basically, if you have a fixed CBF with homogeneous parameters zeta and eta, so all the robots have the same ones, then you can either think of choosing more conservative parameter values. What that leads to is very inefficient trajectories, so they'll be making very large detours around everything they see around them. Or you can try to go for more aggressive parameters, but that might lead to infeasible controls. So you're telling your robot to execute accelerations it's physically not capable of doing given its dynamics model. So those are our two extremes, and you now have to find a sweet spot somewhere in the middle that leads to completion of the task. And that tuning process is quite hard. So, and especially it's static. So what have we done? How have we done? So we decided to model a time revolving system where zeta and eta are being found in real time as a function of local context. So what do I mean by local context? So phi here is our GNN, which is going to be taking as input the state of myself. So I'm the robot computing the parameters for my CLF CBF control. I'm going to be taking in the positions of all the robots I can directly communicate with. So my neighborhood, that's my X sub J. And I'll be computing as a function of the obstacles I can see in my immediate vicinity as well. So that's P sub L. And I'm going to be finding the parameters of this GNN in order for me to be able to run this GNN in real time, predicting my values of zeta and eta at every iteration. And so as you can see here in the results is, so that's a play out of an actual task we had our robots run through, so from origins to destinations. And this is what the two parameters look like as you play through the system. And you can see how they're evolving through time and how our function found that actually they need to evolve through time if they're supposed to solve the system in this particular way. So we then thought, well, how about if these are valid parameters, how about we just take the min and the max and we try to fix them to those values and see, well, maybe that also is enough, and maybe our hypothesis of time-varying parameters and heterogeneous parameters isn't even needed. So we took the mean and max values of agent 3, because every agent here had different plots, and we deployed it on the system and we played it out to see what would happen. And you can see here in both versions, so the min, which is the conservative version, it didn't complete. So the agents, some of them were taking very big detours, so big that the other two agents couldn't even move. They didn't have enough space. And in the aggressive version, they came into a deadlock here because the accelerations that were commanded became unfeasible and there was nothing the robots could do. They couldn't proceed with their motion. So this is showing that even if the spans are valid, fixing them and deploying them homogeneously across the robot team doesn't seem to provide satisfying solutions. So there doesn't seem to be a shortcut that seems immediately viable here. And so we run with our system and we can then compare it in some various tests. You can see how our online CBF, fixed CBF versions perform quite differently for the same setup, and you'll have to trust us that we really tried very hard. We did exhaustive parameter sweeps for the fixed CBF, and they didn't seem to find values that ever concluded in these particular layouts. So you can see these are challenging layouts with regularity and symmetries, which make it difficult for the CBF to be conflict effectively. And then obviously we went back to our original scenario and deployed our online GNN onto the robots. And what happens now is that they're elegantly able to deconflict with each other because they're running these systems in real time. The two parameters that are part of the CLF CBF are heterogeneous across the robots, and we have very nice prioritization taking place across the robots, and we can now complete the task. What I particularly like about this solution is, for those who are paying attention, it's a hybrid solution, right? So we have all the guarantees that are given to us through the CLF CBF paradigm, right? We have safety and completeness and reachability, and the learning bit is only a part in the middle, sandwiched in between all of that is producing our parameters. So we inherit all the guarantees, yet we actually make it more deployable to real systems due to the tuning that we're doing. Okay, so far I've been talking a lot about GNNs, but homogeneous GNNs. So what do I mean by that is, during the training phase, we think about a GNN as something that we're training, and we have one set of parameters, and that's the same set of parameters we're going to be using on all the robots. This is interesting for many reasons. It's efficient because we're doing parameter sharing across however many n robots, permutation equivariant, and we can even emulate heterogeneous behaviors through potentially what I showed you before, or through explicit indexing and so on and so forth. But there are some instances and some examples where using heterogeneous interaction strategies is actually interesting. So by heterogeneous, what I mean here is, for the same observation in our system, our GNN or model is going to output a different action. So different robots for the same observation might be doing different things.
There's no more parameter sharing. We can now potentially train these systems in a decentralized manner because they don't need to share parameters. However, we're not permutation invariant or equivariant. This leads to an observation state space explosion, and it's also clearly less sample efficient. So there are downsides. There are clear downsides, especially in terms of training, and this is a big negative because training is often already complicated enough for multi-robot systems, so why make our lives even harder? So we started to think a little bit about, well, why might we want to have heterogeneous systems and what are the benefits going to be? So I already showed you a little bit how heterogeneous behavior can facilitate the coordination of complex control tasks, albeit the GNNs before had the same parameters. However, the resulting behaviors were heterogeneous because they were being tuned in real time, the CBFs. But what I can also show you is how heterogeneity confers resilience. And I'm also going to talk a little bit about, well, once we've shown that heterogeneity is actually useful, how do we actually measure? So I'm going to speed up a little bit because I see it's almost 3 o'clock, but hopefully I can give you some insights into what we've been thinking about in terms of heterogeneous control. So one thing that we've been able to show, and I'm going to give you the insight straight out, is heterogeneous policies can in some cases really facilitate zero-shot transfer of policies that were trained 100% during simulation. And here's an example of an instance where this occurs. So we want robots here to learn, to move to their opposing positions in this kind of constricted hallway scenario. The robots don't actually know where they have to go, but they know they have to move in that direction. And all they can observe is the relative position with respect to the other robot, and that's being sent to them through communication. Now we train this policy in simulation with a heterogeneous, so 2 different graph neural networks we deployed on the real system, and it works out of the box. With homogeneous policies where we constrict the parameters to be the same, in simulation it works just fine. But as we move that policy onto the real robots in the zero-shot transfer, what you can see happening is the robots, they start getting very confused at the center point. And they start engaging in some sort of switch backwards and forwards type behavior. And the reason for this is because they were trained on these relative observations of, action, speed, velocities, and these tend to be a little bit noisy in the real world, they don't really know what role they're supposed to take anymore and which way they're supposed to go. So the resilience of a system, if you do zero-shot transfer and you need clear role separation, requires heterogeneous neural networks and heterogeneous policies to ensure the stabilities of these policies as a function of the noise that you encounter in the real world. And so even if we train the systems with noise in simulation, you see a drop-off of performance. And that was really interesting to us. So there's really no shortcut you can take here. And you can scale the systems up to even 4 robots. And again, here the heterogeneous strategy really does seem to perform better in all of these cases, really providing a key benefit in terms of resilience and robustness as you transfer and deploy collaborative type behaviors to the real world. And the last thing I want to talk about is basically, well, if we've shown or if we're convinced that heterogeneity provides a benefit, then perhaps we can try to measure. And perhaps we can try to measure as a function of how different the robots are, how much better they perform. And so the first thing that we need to do here is, maybe I can just go back here, is we need to devise some sort of function that maps a set of policies to a scalar. And that scalar is basically going to tell us, okay, this is how much different your system of robots are. That's your heterogeneity value. Okay? And so what Matteo, one of my PhD students, came up with is what we call system neural diversity. So this is basically going to be measuring the average behavioral distance over unique pairs of agents in our system. And it's a very simple formula up there. It depends on a function dij, which is basically a diversity metric or a distance metric between pairwise agents. And properties of this SND are, well, it can do a number of things. It varies in the number of equidistant agents, and it can measure even behavioral redundancy. But what's key to this whole thing is, well, what are we going to use as our distance metric? How do you measure the distance between 2 action policies? And so what's key here is that our policies are basically outputting multivariate Gaussians, right? And so we use that insight to say, well, given that we know what they're outputting, all we need to do is be able to measure distances between probability distribution functions. And so we're using the Wasserstein metric, which what it does is it measures the minimum cost required to move a probability mass from P to Q in an optimal transport problem. And it's a very elegant metric and has very many elegant properties that make it stand out with respect to, for example, say the KL divergence. And our distance metric is actually a proper distance metric. So it's non-negative, it has identity of indiscernibles, it's symmetric, and it respects the triangle inequality. The only key challenge we need to overcome is how do we actually measure it? Because we're running a system that is stochastic and all of that, we decided, okay, we're going to do Monte Carlo sampling of the observation space via rollouts in the environment, collecting our subset O here, which then becomes our discrete interval, and hence can compute the distance metric and include the amount into our SND and compute the SND for any training scheme or any executed task. And so here are a couple of experiments that we perform. So the first one, a very simple one, is a proof of concept. So here we have two robots that are tied together through a rod. They cannot actually observe the robot size, which is key here. And they have to learn through training how to fit through and find themselves on the position of those two green slots on the top. And so clearly this is a task you can only solve with a heterogeneous policy because the robots they have to learn expert roles, right? They have to learn, I'm the big robot, I'm the small robot, I always have to go through the big gap, or I always have to go through the small gap. And so the insight here is that our SND, if it's greater than 0, when the heterogeneous paradigms obtain higher rewards than the homogeneous one, this indicates that heterogeneity enables and is necessary for performance. So the combined performance and SND plots tell us exactly what the task needs in order to be able to solve it. So this is a cool insight, but we took it a step further. And we designed this task where we have two agents that undergo disruption during training. So here we have this kind of setup where we have two robots, or they're kind of two drones that are flying in wind. They don't observe their shapes, but one of them is triangular shaped and deflects wind, and the other robot can lie in its shadow. And they basically have, and the reward here is going to be a joint reward, basically representing the amount of deflected wind as a group, right? So the more wind that they deflect as a group, the higher the reward, the better they can fly as a group. And so what they have to learn here is, oh, I'm the round robot, I'm the triangular robot, I'm the one that has to move under the round robot. And so what you can see happening here is the wind starts, well, both homogeneous and heterogeneous policies start to improve performance. They learn how to, position the robots. The homogeneous one is more like 50-50, right? That's why it's about 0.5. Sometimes the right robot goes into the shadow, sometimes it doesn't. But the heterogeneous one is really the one that learns to place the deflecting robot on the top. When the wind stops, the reward goes down to 0 because there's no wind, there's nothing to be reaped from the system. And when the wind resumes, what is really interesting is you can see the heterogeneous policy has no more learning curve and is straight back up at the maximal reward. Now what the SND shows us, and that is what's so interesting, is in this phase where we have no disruption, we still have diversity in the system, even though the robots are doing the exact same thing, so basically nothing. There's no disruption. And we call this latent resilience, because the robots have learned we have to be different. We have to be complementary to each other, because we don't know what's going to happen next, because if we're a diverse system, we're going to be more resilient to disruptions. That's what we call latent resilience. And only the SND metric is able to expose this latent resilience. And we found this really, really interesting. So basically the insight is, in cases where the task undergoes repeated dynamic disruptions, the SND is able to expose how heterogeneity allows the agents to learn and maintain latent skills for resilience. This is something we really found interesting because it somehow mirrors what we see happening in nature as well. And we can repeat the same insights with the same task I showed you before, where the gap now becomes the dynamic disruption because we can narrow it and increase it as a function of time. And the exact same latent resilience pops up. So to sum this up, we're very excited about heterogeneous agent policies. So this brings me to the end of my talk. I just want to spend a few minutes wrapping up with a few take-home messages. So first, I hope that I've been able to show you that graph nets are very interesting for learning interactions in multi-agent systems and allow us to produce differentiable communication architectures with scalable policy execution in decentralized systems.